All right. So, for all of you that were not in class on Wednesday, and unfortunately that was a lot of you, again, Wednesday, March 22nd, we went over the midterm and we continued chapter 8, basically starting this lecture, lecture 14, which we're finishing up, has a homework assignment for homework number 4. So we were covering the second part of the flight instruments for the six-pack, specifically the gyroscopic instruments. We talked about this already, so I'm just going to skip very quickly and skim through the slides. So we talked about the operating principles of gyroscopes. We talked about rigidity in space and how that's affected the reasoning behind the fact that we want to use gyroscopes basically as a frame of reference, and in particular the plane on which a gyroscope is rotating. If that plane remains in a fixed position, then we can use it as a reference. After rigidity in space, we talked about precession, and to better understand the idea behind precession and how pitch and yaw, or yaw and roll movement are actually coupled together, we watched a video on YouTube. And those of you who were not in class on Wednesday can actually go on YouTube and watch that video. And I encourage all of you to actually watch it again, because this time you will actually have audio, and so you can listen to whatever the guy is talking about. All right, so in the video that we watched on YouTube, you might have noticed that the person was trying to move the gimbal of the gyroscope before it was actually turned on, and then he hooked up electricity and the gyro started rotating. Well, that is because instruments that function thanks to a gyroscope can have a different, let's say, power source for rotation. In the video we saw, it was an electrical source. So remember, that will come from the electrical system that we have already covered with chapter 7. However, there are other ways of rotating a gyro, and some of them use what we call a vacuum or pressure system. Generally speaking, you want to have redundancy at a very minimum of turn indication, so that you can have multiple instruments, some of them relying on the electrical system and some of them relying on a vacuum or pressure type of system. A vacuum or pressure system is rotating a gyro by drawing a stream of air against the rotor vanes. So the geometry of the rotor is quite different. The one we have seen in the video, that was a smooth wheel that was rotating. In vacuum or pressure systems, we're going to have vanes built into that rotor, so that basically you have a kind of a water wheel that is not activated by water, but is activated by a stream of air. You can see a video, so I posted here another link to a YouTube video that shows you how a vacuum gyro rotates and how that system is designed. The one thing you want to keep in mind is that whenever you have that type of system, of course you're going to have a gauge that will tell you what is the pressure within that vacuum. It's not really a vacuum, it's not absence of air that we're talking about. It's a very low pressure type of system. We're talking about 4 or 5 inches of mercury, and you can compare that to the number that you all now know by heart, that 29.92 inches of mercury, which is the standard value associated with sea level. So it's a much, much lower pressure. And the idea is that you want basically the air to be sucked in the system. And I think that the final sentence that I have right here is not maybe that accurate. If suction pressure is not low enough, actually instruments do not work well. Anyway, you can watch the YouTube video, and this is as much as I want to cover in terms of the operating principle and the theory behind these instruments. So let's actually go and look at the gyroscopic instruments. So we briefly talked in class already about the turn coordinator and the slip indicator. So the turn indicator, which is the one you see on your left, this guy right here, initially shows you roll rate. So this airplane right here is basically going to rotate, and we're going to see it in a second. And once it starts rotating, it indicates the roll rate. So it indicates how many bank degrees you achieve per second. Remember, we talked in class about the difference between roll rate and turn rate. The roll rate is the degrees of bank, so the rotation around the longitudinal axis of the airplane. And then we talked about the turn rate. The turn rate was still some degrees per second or per minute. However, with regards to a circular flight path, so the flight path that you will follow during your turn. So for those of you who were not in class on Wednesday and missed the explanation with me impersonating an airplane, I strongly suggest that you either watch some videos or you actually read your textbook about the difference between roll rate and turn rate. So the main difference between the two, other than the fact that the turn coordinator actually shows you a very small airplane also, is that the turn coordinator at the beginning of its functioning from level flight to a turn will show you also roll rate. Both instruments will indicate turn rate, but only the turn coordinator can show at the beginning of the bank the roll rate. They both provide you turn direction and quality, and I want to talk to you a little bit more about this quality. Quality in relation to a turn means understanding if your turn is coordinated or not, and we're going to learn in a second what that means. And the coordination indication is achieved through the inclinometer, and we talked about the inclinometer already during class on Wednesday. The inclinometer is this part right here, and there is an inclinometer in both the turn coordinator and the turn and slip indicator. Whenever you are turning, if the ball is centered, then your turn is coordinated. If the ball is to the left or to the right, the turn is not coordinated and will either be a slipping turn or a skidding turn, and we're going to learn about that in the next slide. The one thing I want to remind to you, and we already pointed this out, is that the inclinometer and the ball that moves within the inclinometer is not based on the gyroscopic mechanisms that we talked about before. So this is just some damping fluid, and the ball moves due to centrifugal force and also actually due to the horizontal component of lift. And that's all there is to it. There is no weird mechanism or mechanical parts moving behind the functioning or the operating principle of an inclinometer. Now, let's look at what coordinated turn means and what are these slip and skid conditions. So the first terminology that I want you to learn is what a standard turn is. And by definition, a standard turn is one that achieves 3 degrees of turn per second. So basically, if you were to go in a circular flight path, where a circle, of course, is defined by 360 degrees rotation, and you do 3 degrees per second, if you do your math, you get 120 seconds to actually complete that circular flight path, and so that's 2 minutes. So a standard turn is one that will lead you to do a complete turn in 2 minutes. Now, if you look at your turn coordinator instrument, which is the one with the small airplane, you have basically two positions. Here, what we see right here is a wing level. These marks right here that you have in all of them, so I'm not pointing to any specific one of these things, is the wing level position or 0 degrees bank. And then you have two marks, one to the right and one to the left, that indicate the standard rate of turn. So that means that if during your turn you are in a situation like this one or this one, you are achieving a standard rate of turn. So in 2 minutes, you will complete your turn. Now, the standard rate of turn is not the same thing as coordinated turn. So remember that they're two separate things when FAA exam questions pop up. So what is a coordinated turn? A coordinated turn is a turn where the aerodynamics forces are balanced. More specifically, which forces? Well, the horizontal component of lift and the centrifugal acceleration produced during the turn, which is actually due to the inertia of the vehicle. And what we said before is that the inclinometer shows you when the turn is coordinated or not. So let's dig into this, and you will need to remind yourself about what we learned when we talked about aerodynamic forces, and especially different components of lift when the aircraft is in a given attitude. So we're no longer talking about level flight, now we're talking about turn, and that means that lift is not acting simply vertically. So it's not going to be only opposing weight. So let's delve into that discussion so that we can learn what slip and skid are and also what a coordinated turn is. So if we look at any one of these figures right here in the bottom, when you are achieving a turn, and we have learned, remember when we talked about control surfaces in chapter 6, that to achieve a turn, what we want to do first is bank the aircraft, and then we're going to use our ailerons to do the banking, but then we're also going to use the rudder to turn the airplane. So what we learned is that whenever we are in a banked configuration, lift acts basically perpendicularly to the plane identified by my wing. And that means that I have different components to lift. One is a vertical component, and this component is what balances weight. And we talked about this a lot. Remember that discussion on the load factor when we said that during a turn, the load factor goes up, and the load factor can also be read as how many times my weight I have to produce lift for. Remember we said, well, if you're in a turn configuration, in a turn attitude, then all of a sudden only the vertical component of lift will be balancing your weight, and so the total lift will be higher than the actual weight. How much higher? N times higher, when N was your load factor. So in turn, you have a vertical component of lift that is what is balancing out weight, but you also have a horizontal component of lift. Now, this horizontal component of lift is what allows you to actually turn, is what pushes your airplane towards the center of the turn so that you can actually achieve rotation or turn in that direction. And it's balanced, or better, we would like it to be balanced by the centrifugal force. The centrifugal force, if you've studied physics, you've learned that this is kind of what we call an apparent force. It's not a real force. It's due to inertia. So whenever I want to give movement to an object that has mass, that object will have an inertia. So somehow it will resist to that movement. Whenever that movement involves a rotation, you have what we call a centripetal acceleration, which is what would push the airplane towards the center of the turn. And in this case, that will be kind of what the horizontal lift component is doing. And by inertia, you will have an acceleration that is generated by reaction for Newton's third principle, which is a centrifugal acceleration or a centrifugal force. So basically what is going on, even if you have not understood what I just said because you haven't taken physics yet, is that you will have a horizontal component of lift whose main task is that of balancing out this centrifugal acceleration, which becomes a force whenever it's applied to a mass, in this case the mass of the airplane, that tends to push it for remaining in actually the current flight path, which is generally straight if we are considering level straight flight. All right. So a coordinated turn, we learned in the previous slide, is one in which the aerodynamics forces are balanced. And that means basically that this horizontal component of lift, right here, if I get my cursor back, this horizontal component of lift balances, so exactly matches the centrifugal force. If that thing happens, so they're both equal, then you will have a coordinated turn. Now, when that doesn't happen, you have either a slipping turn or a skidding turn. In a slip turn, which is the second condition that we have here in the center, the horizontal lift component is actually higher than your centrifugal force. And this means that the airplane tends to slip towards the center of the turn. And then we have the skidding turn, the final one, in which the centrifugal force now is higher than the horizontal lift component. So in that case, we say that the aircraft tends to skid outward towards the outside of the turn. So I want to repeat all of this, but now from the pilot's perspective. So right now we're kind of looking at the airplane from the front, and this airplane is kind of coming straight at you out of the slide, and it would be rotating towards a center that will be somewhere like here, or here for this one, or here for the first one. So it will be rotating, let's see, if we were looking from the top, from here, it would be rotating clockwise, or it's moving out of the slide and towards the left, okay? So that's kind of the rotation that is going on in this picture. Now, let's look at it from the pilot's perspective. So now I want you to think of yourself as the pilot sitting inside the airplane, and this slide, and I have the credits where I took the pictures from, shows you what is the pilot perspective during slip and skid. So basically what happens when you learn about how to achieve a coordinated turn and how you actually use the rudder to ensure that your turn is coordinated, and we'll talk about the rudder in a second, you need that, basically what you need to do is feel the airplane. The instructor generally doesn't want you to sit straight and try to remain to sit straight. They want you to basically ride the airplane, because that way you can feel the acceleration and understand if your turn is coordinated or not. So in this case, we are the pilot, and we're doing, if I'm looking from the pilot perspective, it's exactly actually the same situation we had before, but now we're looking from the other side. We're looking from the cockpit. So in this case, my airplane will be going into the slide, and it will be rotating towards the right, okay? So now we have again the three conditions. Let's look at the center one. So this is a coordinated turn, and what you will see if you actually start your training and you get to the point where you learn coordinated turn, we can see on our turn coordinator that the ball is centered if the turn is coordinated, which means that the horizontal component of lift is balancing out the centrifugal force, and what you feel is actually a force straight down that pushes you onto the seat. Now on skidding, the skidding is when the centrifugal force is actually higher than your horizontal component of lift. In this case, we have the centrifugal force that's pushing towards this direction, and the horizontal component of lift that is pushing in this direction. So this side for horizontal component of lift, towards the right, and then towards the left, the centrifugal force. So during skidding, that centrifugal force is higher than the horizontal component of lift. And what you see in the turn coordinator is that the ball will be outside of the turn. So you cannot say left or right for a slip or skid, because it always depends the direction in which you are rotating. So you always want to look at the situation of your airplane and see that this is indicating, it's actually pointing toward a standard turn. So we're doing a full turn, a full 360 turn in 2 minutes, because actually it's pointing towards the standard rate of turn. And this tells me that this is a turn to the right. So during a turn to the right, if we're skidding, the ball is to the outside of the turn, so the ball is going to be on the left. Vice versa, if I were to turn towards the left, a skid would have the ball to the right. Okay, so skid means that the ball is going to be to the outside of the turn. So in this case, for a right turn, the ball is going to be on the left, because the centrifugal force, which points outward, is higher than the horizontal component of lift. Now, if we look at the slip situation instead, now what you will feel as a pilot is actually a sideway acceleration that pushes you inside of the turn, because the slip condition is the condition in which the horizontal component of lift is higher than the centrifugal force that pushes the airplane outward. So in this case, it's still the same right turn, so you can still see the same indication in terms of the small airplane that we see on the face of the turn coordinator, but now the ball is going to be to the inside of the turn. Okay, so now we've seen about skid, slip, and coordinated turn. What do you do about it? So the whole point is that you learn about this because you want to correct slip and skid. And why would you want to correct it in the first place? Why is it a bad thing? So to correct it, we use the rudder, as you might have learned when you were reading chapter 6, and hopefully you kind of have this idea that to achieve a turn you have to use in conjunction both the ailerons and the rudder, because hopefully you were paying attention when we covered chapter 6. However, if you still don't know and have no clue about that, this slide might help you a little bit about what is going on. So, however we achieve a turn, the flight path is that of a circular turn about a point. So we're turning around one point, which is the center of the turn. However, only this situation right here is a coordinated situation. In a coordinated situation, the nose of the airplane is actually pointing in the direction of the turn, or in more technical terms, the direction in which the nose is pointing is always tangential to the flight path. Okay, so you can imagine this turn to be actually just a simple circular line, and the nose would always be aligned with that flight path. Now, whenever you're slipping or skidding, that is not the case. So in this case, you have the airplane slipping, and it's very interesting to do a comparison between where the nose is pointing and what is the acceleration that you feel in terms of the pilot. So this situation right here, although the nose is pointing outward, so the nose is pointing outside of the turn, this is the slip situation. What you feel in this situation is actually the airplane is slipping within or inside of the turn, and you can see it better here maybe. So this is the view within the cockpit. Look at the sunglasses. They want to show you that the acceleration you feel is toward the inside of the turn, and it's kind of the opposite, right? So the acceleration you feel and the aircraft will tend to slip inside of the turn with the nose pointing outward. And you can actually see right here that the ball within the inclinometer, this is a right turn again, it's actually inside of the turn. So see, it's almost touching the wing of the small little airplane that you have in your turn coordinator. Again, this one is the coordinated case, so you see that the ball is perfectly centered, and that means that your sunglasses are actually not moving at all, because the acceleration that you feel in this case is not due to any centrifugal or centripetal acceleration, because those things are balanced out by the horizontal lift component. So all you feel is kind of the gravity pull, which will pull you exactly through your seat. So that's the only thing you will feel, and ideally in a perfectly coordinated turn, your sunglasses wouldn't move at all. And this situation is a situation of the skidding turn. In the skidding turn, now you have the centrifugal force that is higher, and so you feel an acceleration towards the outside of the turn. So it's kind of defeating gravity, as you can see that the sunglasses are moving upward. You will see in your inclinometer that the ball is outside of the turn, and as we did with the slip, also for the skid, the nose is pointing opposite to that acceleration. So the nose in this case is pointing inside of the turn, and the airplane is skidding towards the outside. So how do you correct with it so that you actually are always in this very nice situation? Well, the strategy, so that you can remember, is what we call push the ball strategy. So you have to use the rudder, because you can see the problem is where the nose is pointing. So you want to correct the direction of where the nose is pointing. That requires you actually to control yaw. And we know that that is a rotation around the vertical axis, which is controlled by your rudder right here. So you will need to control the rudder, which you do by pushing the pedals that you have in your cockpit. Which side of the pedal, which pedal do you push, left or right? Well, the strategy to remember that is push the ball. You want to push the pedal on the side where the ball of the inclinometer is actually lying. So right here, the ball is to the right, so you're going to use right rudder. Here you have a coordinated turn, so no need for rudder. And right here, you're going to push the ball that is on the left, so you're going to push the left pedal. All right, this is kind of the very first and simple view that I'm going to give to you about slip, skid, and coordinated turn. Of course, it's more complex than that, and it can become more complex, especially when you don't know about this, because all of a sudden you don't remember which side of the rudder to push. So maybe you have this situation, but what you need to do is not pushing the right rudder, it's actually pushing less the pedal on the left. But you'll learn about that when you actually start your flight training. So I'm not gonna go into more details about turn indication. So we're gonna jump to the next instrument, which is much easier to read, or I think at least it's much easier to read, and that's the attitude indicator. The attitude indicator has basically a miniature aircraft, which is this thing right here, that yellow thing, and a horizon line to display the attitude of the airplane. And by attitude, I mean displaying pitch, so whether we are climbing or descending, pitch up and pitch down, and to display roll, so bank and how many degrees of bank. So we learned about a few things, and specifically we learned about rigidity in space. So I'm hoping that you can actually fully understand this sentence, because it says that the attitude indicator functions thanks to a gyro that spins in the horizontal plane. And that horizontal plane of rotation is used as a reference for the horizon. If you remember rigidity in space, we know that plane of rotation will remain horizontal no matter the movement of the frame of this universal gyroscope. Okay, so how do you read the attitude indicator? So we get to the practical things about this instrument. Well, basically, let's look at this right here. This situation right here is a straight and level flight. How do I know that? Well, for instance, the first thing I want to look is I look at this red or orange triangle that I have right here. That is my pointer. So it's not really that white, it's more this one. So the pointer tells me how many degrees of bank, so roll, I am actually in. And the big white triangle stands for 0. And then you have different tick marks, and you see 10 degrees, 20, 30, 45, 60, 90, so on and so forth. So basically, whenever I am aligned with the big white triangle, I am at 0 bank. So right now, I'm not turning. Also, the wings of my airplane are actually aligned with my horizon. So that means that I'm neither climbing up nor descending down. So my pitch is also 0. And that means that I'm in straight and level flight. Now, whenever I will be in a pitch up configuration, which implies a climb, I'm going to look at this row right here on the top. So whenever that happens, the wings, or better, there is actually a central pointer right here, is going to be within the sky, so within the blue part. So whenever that small dot in the center is within the blue part, it means that you're climbing. Whenever that small dot that it's in the center of your miniature airplane is within the brown part, it means you're descending, you're moving towards the ground. Okay? So bottom here, we have some sort of descent. Up here, we have some sort of climb, and that's due to the fact that that small point in the middle here is pointing in the sky, and here is pointing actually on the ground. What else is there? It's not just pitch, it's also about roll. So let's look at roll alone. So roll alone basically will mean that this miniature airplane will either bank to the right or bank to the left. In this situation right here, you have a level left bank. Why is that? Well, if you look at the central point right here, and actually let me go back one slide so that you can see that small pointer. So I'm talking about this little guy right here. Okay, so that small pointer, it's actually exactly on the horizon line. So that means that you're still flying level. You're not changing your altitude. However, my orange pointer, so that small orange triangle that we talked about, now is indicating a left turn to the first big tick mark. This first big tick mark is actually 30 degrees, if you see it right here. So this is 30 and that's 60. So you're actually in a level left bank of 30 degrees. On this side, same thing to the right, and actually also shows you the airplane, all right? So again, that central pointer is on the horizon line, on the horizon line, and your red triangle is pointing to a 30-degree right bank. So now you can actually understand the first row and the final row right here that are combining both climb and descent with bank. So right here, you have a straight climb. See that the bank pointer is actually pointing towards 0, so you're not banking, you're not rolling, but you're climbing because you're pointing in the sky. Here, you're still pointing in the sky, so you're climbing, but you're also in a left bank attitude, and here you're also in a right bank attitude. And same thing for descent. Descending you with a right bank and descend with a left bank. Okay. And this is as much as we're going to cover for now about the attitude indicator. Oh no, actually one more thing. You can see right here there is a knob. And I don't know, or maybe, let me go here. Okay, so the adjustment knob is generally in the middle right here. That's used for calibration. So I cannot really exactly read what this one is, but it's this thing right here. That adjustment knob is for calibration. It's basically what allows you to align the wings of this pointer with the horizon. So it's a calibration mean. Okay, so let's go to the next one, or next and last one, which is the heading indicator. So the heading indicator looks like a compass, but it is not a compass. So that's very important. We're going to finish this lecture by talking about the magnetic compass, or in general magnetic instruments. And the heading indicator is not one of them. The heading indicator is a gyroscopic instrument, and it's a mechanical instrument, and actually it's one of the most complicated gyroscopic instruments, because if you look at the way it is structured, and you don't need to know the details about this, but you will see that the gyro is rotating in a vertical plane. And what you want to know with the heading indicator is, of course, the heading, so where you're going. So what you want to read is a direction. So the heading indicator is displaying yaw, and it's displaying you the direction in which you're moving, you're heading. However, this gyro is rotating in a vertical plane, so somehow you will need to have gears that translate that motion in a vertical plane into a reading of yaw. Okay, why do we have an heading indicator if we already have a magnetic compass? So we will learn this in about 10 minutes, but it turns out that a magnetic compass is subject to a lot of errors. Okay, and so you want to keep your heading or turn to a heading more precise, and you can do that by coupling the use of a magnetic compass with that of a heading indicator. However, also a heading indicator is not super precise, and that's due to two main problems. One of them is a precession error that is mostly due to friction. So if you do not adjust your heading indicator, so let's say that you want to fly north, and you think that your heading indicator is pointing to the north, and you keep following that, and making sure that you're following that north, it turns out that within a couple of hours, that thing will have drifted by a lot. Precession errors happen over a long period of time. However, what really makes the heading indicator not being precise is that Earth rotates. So if Earth is rotating, and if you know your math, and we do one revolution every 24 hours, that means that we're rotating 15 degrees every hour. So you actually need to adjust your heading indicator during your operations and during flight. Otherwise, within 1 hour, you have accumulated at a very minimum 15 degrees of error. It is generally more than that, because on top of the error due to Earth rotation, there is also precession. So I'll leave it here with the heading indicator, because before talking more about this, I want to look at magnetic compass. With the heading indicator covered in terms of at least how it looks like, right now you don't know how to use it, and that's normal. We have covered the 6 or 7 basic instruments that you can find in a typical general aviation airplane. We also mentioned that there are general aviation airplanes that are not that typical. They're more modern, and they will come with what we call an electronic flight display. An electronic flight display will look something like this. So this is a picture taken from your textbook of a primary flight display. And you can see that a primary flight display actually combines together several different instruments. For instance, right here you have your airspeed indicator, and this is what we call an airspeed tape because it's just a line that tells you the number with a specific pointer. On this side right here we have a vertical speed indicator, our VSI, and they are somehow, these two tapes are somehow mounted on the sides of what looks like an attitude indicator. And then you also have what it's called the HSI, or horizontal situation indicator, which combines actually quite a few instruments. One of those is the heading indicator, and others that you have not studied or learned about yet. Right here, this thing right here, this small white line, that small like thing that can move to the left or the right of this arrow, is your slip and skid indicator, indicating whether your turn is coordinated or not. So honestly, if you're not an experienced pilot, this is not something that easy to read, but I can guarantee to you that it's easier once you already know how to read the six-pack. If you're a skilled person with the six-pack and then you want to move to an electronic flight display, it will take you some adjustment time, but you will be able to do it quickly. If you learn with this one and then you try to go back to the six-pack because all of a sudden you need to rent an airplane and you don't want to pay an extra $100 an hour because there is an electronic flight display. You care about flying somewhere, so you want the cheapest airplane that you can get. Well, all of a sudden, if you train with this, it might be a little harder for you to go back to the six-pack. So generally speaking, you will start training with the regular instruments that we studied, so the pitot-static and the gyroscopic instruments. Now, this is what we call, as I said, the primary flight display. There are also secondary displays that they generally have multiple functions. For instance, they can display weather, they can display traffic, they can display your navigation route. And this is kind of the overall view of a cockpit, of what we call a glass cockpit. And what you can see is actually that there are also redundant systems. So for instance, if you recall, this is, just by looking, see that there are the color codes. This is your airspeed indicator, and again, this is your attitude indicator, and this is your altimeter. So you will have backup instruments at the bottom of a glass cockpit, and that's required by law. Okay, so this is as much as I want to cover about the electronic flight display, and you can read more about it. Final stuff, and now we're getting to the good stuff, magnetic instruments and errors. All right, so it may come to you as a news, but Earth is just like a giant magnet. The core of our planet contains melted ferromagnetic metals, and that means that Earth is actually a giant spinning magnet. If you have taken physics, you already know about this, but if you haven't, you will learn that a magnet is going to generate a magnetic field with an associated magnetic flux. So what is that? I don't want to do any physics here. I want to keep it simple. Basically speaking, each magnet has two poles, a south pole and a north pole. And it generates this magnetic field which moves coming out, where is my arrow? Right here. Coming out of the north end and moving into the south end of the magnet. So this would be kind of the magnet. Now, in this sketch right here, this would be Earth, which is really not that circular, but let's assume it's in a perfect sphere. And we will learn about the fact that the true north and the true south of Earth, so what we have as North Pole and South Pole, are actually not aligned with the magnetic North Pole and the magnetic South Pole. But before we learn about this and what this means, let's look at a magnetic compass. So a magnetic compass is one of the required instruments for both VFR and IFR flight. If you recall it from our first two lectures, VFR is visual flight rules and IFR is instrument flight rules, and that really depends on your rating as a pilot. As a private pilot, you will only be allowed to fly VFR, so visual flight rules. But for both, a magnetic compass is required, and this means that there is a magnetic compass in every single airplane, basically. A compass contains a magnetic metal. So all magnetic metals basically are able to feel a pull towards any magnetic source. And if you have learned this in high school or in your physics classes, the rule is that opposite poles attract each other. So if I have a magnetic piece of metal, it will have a north and a south end, or a positive and a negative pole. And the north pole of my little magnet will align with the south pole of Earth's magnetic field. And notice, if we go back to the south pole of the Earth magnet is actually what we call the magnetic north, while the north end, or the north pole of the magnet, is what we call the magnetic south. Okay? So now the north pole of my metal will align with the south pole of the Earth magnet, which means that it points to the north. Now, how do you use that thing? I'm sure that all of you have seen the regular compass that you can use for, I don't know, going somewhere when you're walking on the ground. I remember when I was in high school, we did this exercise of using a compass. Like, they brought us onto a mountain and left us there and saying, okay, we want you to get back to camp, and you can use this chart and this compass to get back. I don't know if you do that kind of challenges around here. But the idea is that actually a magnetic compass that you will find in an aircraft is slightly more complicated. A compass in an airplane has a graduated scale, which is this thing. So it's basically a card. Forget about this for a second. So it's a card that it's marked with cardinal directions, so north, south, east, and west. And then it has tick marks, numbers, for each 30 degrees between the cardinal directions. So right here, this is north, this is 30 degrees, this is 60 degrees, and if you can read right here that it's a 33, that it's for 330. And in between these main 30 degrees tick marks, there are also other tick marks. So each long one is 10 degrees. So we have 10 degrees here, 20, which is kind of covered by the line right now, and then 30. And then you also have short tick marks, which are for 5 degrees. So I can also here read 5, 10, 15, 20, 25, 30, 35, 40, 45, and so on and so forth. Note, and this is why it gets complicated, that the card appears backward. So if this is north and this is 30 degrees, this is 60, this is 90 right here. 90 will be east. Notice that east is to the left. So east will be what you generally would expect west to be. And at the same side, if we have same way, if we have north here, then we have 330, 300, and then 270, which will be west. And west should be on the left, but it appears on the right. Now, the reason for this is that in truth, the card remains stationary, but it's the compass housing, so it's this whole thing that is rotating around the card. So it only appears to you backward, but you actually read the correct indication. And again, once you start flying and you start your training, this will all become natural to you. All right, now back to the discussion that the true geographic north actually is not aligned with magnetic north, and that is due to how the metals in the core of Earth are actually placed within the core of our planet. So there are a few issues. So one of them is that they're not aligned. So okay, well, there is an error. But it's more complex than that, because Earth is actually not a sphere. So if they were simply not aligned, I could tell you, oh, okay, the difference between the two is 15 degrees. Yeah, that's great. That's not that great, because Earth is not a sphere. And being not a perfect sphere, that means that also it's not a perfect spherical magnet. So all these lines which symbolize and signify the magnetic field, they are not these very nice shapes. They can be more elliptical in some regions and be more stretched in other ones. They can change shape. So that means that the difference between the geographical north and the magnetic north is actually changing locally as I move on the Earth. Now, terminology. The difference between true north and magnetic north is variation. So that's the first term that I want you to learn, variation. Second thing, variation is only the local difference between the true or geographical direction and the magnetic direction. Okay? So it's local because at every single point is going to be different. And this map right here, which is taken from your textbook, shows you different values of variation. So each of those lines is a line, it's called an isogonic line. So it's a line that basically feels the same magnetic field. And each of those lines has a small number that shows you what is the local variation over there. Okay? So what does this mean for you? It means that when you're flying and you want to account for variation because you want to know where you are, well, you will need to read local variation from a sectional chart. So we will learn about sectional charts after spring break, and we're going to have so much fun with them. And what we will see is that there are lines just like this one, which show you magnetic variation. In this case, this is a magnetic variation of 15 degrees west. Magnetic variation is divided in west or east. All right? So we learned what variation is, difference between the true geographical direction and the magnetic direction. So whenever you're talking something and say, oh, it's 220 degrees, you need also to specify whether you're talking magnetic and whether you're talking true. All right, and we're going to learn that with wind, we're going to learn it with weather, we're going to learn it with runway operations, and so on and so forth. All right? Variation, and then, of course, more errors, deviation. Deviation is an additional error in the reading of a magnetic field. So, what is deviation due to? Well, it's due to flight instruments and electronics. We talked about the induction principle before, and if you remember, we said that anything that is made of a conducting metal or any conducting material, if you have an electrical current flowing in it, it will generate a small magnetic field. Now, that small magnetic field locally will add to the one that is generated by Earth. So it will disturb the reading of the local magnetic field because you will have a sort of interference created by your electronics and anything that is made of a conducting metal and has current in it, because all of those things will generate a magnetic field, including your cell phones, including a walkie-talkie, including your laptop, and so on and so forth. So deviation is not dependent on the geographic location, okay? But it does depend on the aircraft heading and attitude. So generally speaking, depending on the local position of your airplane and its attitude, meaning if it's a straight level flight or if it's turning, the magnetic fields that all these instruments are generating will have a different effect. How do you actually account for deviation? Well, you have deviation errors written in a compass correction card, which looks like this one. And let me go back a couple of slides. This right here, this is a compass correction card. So basically in here, you will write down errors due to deviation. How do you know how much that error is? Well, there is a calibration thing that you have to do, which we see in this photo right here, and it's called the swinging of the compass. So basically what you do, you actually align your airplane with known headings and known directions. So here you have the, like, I don't know how you call this in English, the pointer star or whatever. So you have north, west, east, south, and known headings. You will point the airplane at different headings in a given sequence, and there are regulations for that. And then you will read the reading from your magnetic compass so that you will basically know how much your electronics is disturbing the reading, and you will be able to actually write down what the actual reading is. So for instance, here it's saying, okay, what is the reading when I have my electronics on, when I have my electronics off, and so I can basically combine the two for kind of calibration. All right? So we learned two things. We learned variation and we learned deviation. So now we're going to learn additional terminology and then we're done, which is understanding that you always have to specify whether you're talking about through heading or a magnetic heading. And there are acronyms, of course, for these things. TH stands for through heading and MH stands for magnetic heading. Remember when we learned about runway and we said, oh, runway 21 stands for 210. It turns out that that is a magnetic heading. So 210 means that my runway is pointed towards 210 degrees magnetic. Remember what we learned about wind, and I would say, well, wind is coming from 270. It turns out that it's 270 through, okay? So you will need to know that there is a difference between what you're reading in terms of wind and what is the actual alignment of your runway, all right? How do you go from through heading to magnetic heading or from magnetic heading to through heading? This is your first navigation lesson. You will need to account for errors due to variation and deviation. Truth be told, for your private pilot exam, you will mostly never talk about deviation, but please know that it exists and that there is an error due to deviation, and that error will be indicated in your compass correction card. So what we really want to do is either go from magnetic heading to through heading or vice versa. And to do that, you will need to add or subtract the variation error. What do? Do you add or subtract? Well, there are rules. And this is, as it says here, your first navigation lesson. You subtract east variation to through heading, or you add west variation to through heading if you want to obtain magnetic heading. Vice versa, if you already had a magnetic heading and what you want to find is through heading, then you will need to add east variation or subtract west variation. Oh God, how do I remember that? I'm going to forget. No worries. Your E6B will be always with you, also during your exam. If you turn to the wind side of the E6B, that's the side we have not used yet, on the top, it actually tells you all the rules. And it tells you whether you need to add or subtract west or east variation, depending on whether you're computing the magnetic heading or the through heading. All right, so this is kind of your first intro to navigation lesson. And navigation is what we will cover after midterm number 2. So it's going to come actually pretty soon. The final slide for this is related to additional magnetic errors. So we learned about variation, we learned about deviation. And it turns out there are additional errors that are due to actual accelerations, decelerations, or change of heading, so during turns. And there are different mnemonic rules that you can use to remember them. And one of those is the ENS rule. So this is an acronym that tells you acceleration north, deceleration south. Because it turns out that whenever you are accelerating or decelerating, your magnetic compass will show you an error. Whenever you are accelerating, it will slightly point towards the north. Whenever you are decelerating, it will slightly point towards the south. And this is called acceleration error. And then there are also errors related to turns. When you're turning towards the north, so northerly turns cause the compass to lead. So that means that actually the compass or the housing, or better, the relative movement between the housing and the card, which is connected to your magnetic metal within the compass, leads, so has a faster movement than what you're actually doing. So you basically want to stop the turn before the arrival to the desired heading. And southerly turns cause the compass to lag. A lag is basically a retard. So you want to continue the turn also after arrival to the desired heading. I've wrote you here something simple that is for you to consider. This is a lot of information to digest, a lot of information to take in. Hopefully you will have spring break to reread all of this in your textbook. However, until you actually experience these issues yourself, you can only get what we call the rote level of understanding. Remember that this error exists. If you plan on becoming a pilot, then of course you want to remember, because you will need to take that FAA exam and there will be questions about this. But I don't expect you to actually know all the operating principles behind gyroscopes and all the errors. So you will get questions in your midterm and in your final. So you have to be reminded of the issues that we discussed. However, I don't expect you to actually know how the gimbals and the gears are mounted within specific instruments. I might ask you something like, why is rigidity in space important? So if you don't remember that horizontal plane of rotation, for instance, for the attitude indicator, is used as a reference for the horizon, okay, that's an issue. Now, if you don't remember that there are specific gears for the heading indicator to translate rotation in the vertical plane into a yaw reading, that I don't care. That is too much. As usual, we will have quizzes about this material, so you will kind of already know what to expect in terms of questions for the midterm, just like it was for midterm number 1. All right? So hopefully you get the time to watch this lecture sooner or later before homework 4 is actually due. You will see that you are going to have open-ended questions related to this lecture that you will have to answer. And besides that, I hope you enjoy spring break and have fun, but please be safe. All right. Bye and see you in a couple of weeks.